3 explosions rip from the hidden face of the sun and charge into the inner system like incandescent avalanches. Magnetic fields twist, the corona heaves, and the tiny interstellar visitor they seem to target keeps gliding as if nothing happened. No swerve, no stutter, not even a flinch in the orbit we so confidently predicted. Did the sun simply miss, or did it meet its match? We are going to test that paradox with data, not vibes. Buckle in and tap like and subscribe now so you do not miss the live updates as this story evolves. Start with what is not in dispute. A new object entered our neighborhood on a path that does not close. Astronomers call that a hyperbola, and it means the visitor is not bound to the sun at all. Its eccentricity lands near 6, which is a friendly way of saying gravity barely curves the track. Its velocity relative to the sun hovers near 60 kilometers per second, fast enough to cross an Earth-Moon distance in a couple of hours. It swept inward, through summer, headed for a closest approach in late October, at about 1.35 astronomical units. That is a bit inside Mars, close enough to heat up, far enough to avoid instant ruin. Telescopes did their work. Hubble resolved a classic comet look, a compact nucleus wrapped in a gauzy coma and a tail pointing away from the sunday. The James Webb Space Telescope sniffed the glow and found a surprise. The gas was unusually rich in carbon dioxide, rather than the water and carbon monoxide typical of many comets in our system. That chemical fingerprint suggests either a warmer birth environment around another star, or a long, harsh life where the most fragile ices have already been cooked off. Either way, the composition sets this object apart before the drama even begins. Then came the geometry that makes astronomers groan. From Earth's perspective, the object slid behind the sun into superior conjunction. You cannot watch a firefly sitting next to a stadium floodlight with ordinary optics. So we leaned on coronagraphs, instruments that block the disk of the sun to reveal the fainter halo around it. In those frames, a faint moving smudge traced exactly where the official ephemeris said the object should be, frame by frame, day after day. Confidence grew that the track was intact, even while the object hid in glare. That is when reports began to circulate about the sun throwing not 1 but 3 coronal mass ejections from far-side active regions aligned with the visitor's predicted position. These are not simple puffs of heat. Coronal ejections are magnetized plasma clouds carrying tangled magnetic fields and enormous momentum. When they slam into a small body, they compress tails, strip comas, and in principle they can impart a shove. It might be small in the moment, but it compounds over days. You would expect a measurable drift from the predicted path. Yet when the smudge reappeared after conjunction, it was right where careful calculators said it would be. Not early, not late, not off to the side. This is our paradox in full view. Either the ejections missed, or our size and mass estimates are far off, or something about the plasma dance redistributed forces so the nucleus felt almost nothing. That last possibility sounds audacious. It is also not magic. The moving conductor through a magnetic field can develop currents and forces that act like a spring spread across a vast volume. A coma is not empty. Under the right conditions, it can become an induced magnetosphere. Here is the agreement we make with you at the start. We are not here to sell a miracle. We are here to run a shared investigation. We will keep the emotional voltage high because the story deserves it, and we will keep the explanations plain because clarity is power. We will show why an eccentricity near 6 matters for sensitivity to small forces. We will translate momentum transfer into everyday intuition. We will map the far side of the sun you cannot see and the instruments that let us infer it anyway. And when we speculate, we will say so, then give you the test that could prove us wrong. This is not just academic curiosity. We are climbing towards solar maximum. Big ejections are more common. Space weather hits our satellites and power grids, whether a visitor is passing through or not. If a real electromagnetic coupling can slightly shield or shape forces on a small body, even modestly, that is worth knowing. It would refine our models for comets, for star-object interactions, and for the solar wind that breathes past Earth every day. So the stakes are simple. If 3 immense ejections really cross the path of a 2 to 3 kilometer nucleus wrapped in ionized gas, why is the orbit unshaken? Did the sun miss, or did the visitor meet the storm with physics we have not yet folded into the textbook? Stay with us as we untangle the numbers, confront the footage, and walk the narrow bridge between extraordinary claims and hard evidence. The night it began did not look like history. It looked like another routine passed through a crowded sky, one more set of images from a survey telescope built to find moving things. The Atlas survey in Chile caught a faint smudge that did not belong to the background star field. One frame alone is never enough. Astronomers stack images, blink them, and watch for motion that is steady and real. The smudge moved with purpose. Follow-ups from other scopes snapped into place within hours. Little by little, dots on a screen became a path with meaning. There is a moment in every discovery when curiosity hardens into responsibility. You have positions on multiple nights. You submit them to the clearinghouse that tracks small bodies. Calculators chew on the numbers. At first you expect an odd comet, or a long-period visitor on a stretched ellipse. Then, the fit comes back with a value that makes people sit up straight. Eccentricity greater than 1 means the path will never close. Eccentricity near 6 means the sun is not a home base. It is a buoy the object barely notices as it flies past. The team checked everything twice. Were the timestamps correct? Was the reference catalogue behaving? Could they be chasing a ghost, born from a bad subtraction or a hot pixel? No one wants to raise the flag for an interstellar visitor unless the case is solid. More observatories joined in. Parallaxes from different longitudes helped lock the speed and direction. With each addition, the error bars shrank and the confidence grew. The designation arrived and people began saying the name out loud. 3I Atlas. It felt ciphered and mythic at once. By now, the object had a personality. Not in a sentimental way, but in the way a track on a plot can command attention. It was fast. Relative to the sun, it was moving around 60 kilometers per second. That speed is a clue to its origin. You do not get it from a quiet drift out of our own Oort cloud. You get it from the deeper currents of the galaxy, from the long traffic of stars and their debris. The predicted closest approach to the sun landed in late October at roughly 1.35 astronomical units. That distance is just inside the orbit of Mars, hot enough to wake surface ices, not close enough to shred a body outright. There is a rhythm to nights like these. Someone grabs the early twilight window. Someone else takes the pre-dawn hour. Messages bounce between hemispheres. Observers trade finding charts and short exposure tips that keep the nucleus from smearing into invisibility. Every clean position feeds the orbit fitters, who nudge their models and send back a new ephemeris. The plot tightens. The feeling that you are witnessing a rare visitor hardens into the fact that you are. For most of us, this will happen only a handful of times in a career. The first real look at the body itself arrived through a space telescope's patient eye. Hubble resolved a compact nucleus wrapped in a faint coma. The tail pointed away from the sun, as expected, under the pressure of light and the push of the solar wind. This was not a dry asteroid skipping through. This was something that could sublimate. The James Webb Space Telescope studied the glow and found a mix that leaned hard on carbon dioxide. Water was present, but the signature said carbon dioxide forward in a way that is rare for comets tied to our own Sunday. That chemical strangeness added texture to the object's story. It was not only from somewhere else, it had been processed in a way that set it apart before it ever reached us. With the orbit settled, the timeline became clear. There would be a brief window of traditional observing before geometry turned against the watchers on Earth. In October, the object would slip into the solar glare. Superior conjunction is a sterile term for a cruel fact. You cannot inspect a firefly hugging a searchlight with ordinary optics. Plans shifted to coronagraphs and spacecraft that can stare near the sun by blocking its blinding face. The community braced for a pause in easy data and hoped for a clean handoff between instruments. The mood in those days mixed joy and caution. You do not get to choose which interstellar visitor you meet. You prepare as best you can, then you follow where the photons lead. 3I Atlas gave us a generous approach arc, a clear set of nights for triangulation, and the gift of early chemistry that hinted at an unusual past. It also gave us a test. Could the network of observers on and above Earth keep a thread on a faint target as it crossed the most hostile background in the sky? The answer, at first, looked like a yes. Coronagraph frames began to dribble in with a faint smudge creeping along where the ephemeris said it should. That quiet confirmation set the stage for the turn no one expected. The sun was waking into a more active phase. Far-side regions were building energy. And while our visitor slipped behind the glare, whispers began to circulate that the star had thrown not one, but 3 immense ejections across the predicted path. A discovery that started as a tidy triumph of measurement was about to collide with the volatile heart of a living star. Picture the sun as a giant campfire, and our visitor as a stone you throw toward the glow. A stone in a bound orbit loops back for another pass. A stone on a hyperbola does not loop at all. It sweeps in, curves a little, and is gone forever. That is the shape we are dealing with here. Eccentricity above 1 means open path. Eccentricity near 6 means almost a straight line with only a polite bow toward the Sunday. The gravity well tugs, but at this speed, the tug barely rounds the corner. Speed sets the tone. 60 kilometers per second relative to the sun is not a rumor. It is a freight train through the inner system. At that pace, the distance from Earth to the moon would vanish in a few hours. People sometimes think faster means harder to disturb. Paradoxically, this kind of fast flyby can be sensitive to small sideways nudges. When a path is almost straight, even a tiny lateral push can translate into a noticeable misdistance days later. The sun adds curvature, yes, but the curve is gentle. So if a shove landed near closest approach, we would expect to see a drift accumulate. Now for the energy story, without the math maze. Bound orbits are like marbles rattling in a bowl. You push, and the marble still ends up back in the bowl. Hyperbolic motion is a marble flying across the tabletop past the rim of the bowl. It feels the pull, dips slightly, and keeps going. Astronomers wrap this in the idea of positive orbital energy and velocity at infinity. You can hear the meaning in the words. If you could turn the sun off and let the object coast, it would still be moving tens of kilometers per second out in deep space. That built-in getaway speed is why the sun acts more like a bend than a leash. Where does such speed come from? Not from our sleepy Oort cloud where comets ooze inward. It comes from the larger shuffle of the galaxy, old gravitational kicks, past encounters. The wide circulation of matter through the thick disk of stars. When a fragment takes shape in one system and is later ejected, it can carry away a permanent ticket to elsewhere. That is how a traveller ends up on a one-way line through our sky. Let us translate these ideas into something you can feel in your hands. Imagine sliding a coin across a table so it just grazes a magnet. If the coin is slow, the magnet pulls it into a tight curve. If the coin is fast, it only kinks the path a little. Now imagine a small gust of air hitting the coin while it is next to the magnet. The magnet still cannot trap the coin, but the gust can shift where the coin ends up on the far edge of the table. That gust is the kind of shove a coronal mass ejection could deliver. It is not about stopping the coin, it is about changing the exit lane by a hair that becomes a meter by the time it reaches the wall. Non-gravitational forces already do this to comets. Sunlight pushes tiny grains. Jets of gas venting from warm patches act like thrusters. Astronomers even have standard terms for it. Outgassing acceleration, rocket effect. With careful tracking, we watch small comets arrive a little early or a little late compared with a purely gravitational schedule. The same logic applies here. If 3 massive ejections of magnetized plasma cross the visitor's path, we should expect a measurable nudge layered on top of any outgassing effect. Not a theatrical skid. A crisp, clock-like offset that keeps growing. Perihelion sets the stage for the biggest lever arm. That is the moment of closest approach to the sun, about 1.35 astronomical units for this object. Speeds peak there. Fields are stronger. The coma is most active. The geometry is brutal too, because from Earth the object was near the sun in the sky, which is why we relied on coronagraphs that block the solar disk. If a shove happened then, we would see its echo later when the object emerged back into darker sky and precise astrometry resumed. The ephemeris would require a correction. A few arc seconds now, more later, the kind of drift that keeps orbit fit as honest. There is one more intuition that helps. Think of a river that bends gently around a wide island. A boat racing downstream follows the curve, but only just. Toss a log at the boat and the hit may not slow it visibly. Yet the boat ends up a few boat widths to the side by the next bend. With a hyperbolic track, the solar bend is that wide curve. The ejection is the thrown log. You do not judge the shove by the instant jolt. You judge it by where the boat is when you check a mile later. So the expectation is not mystical. It is practical. A fast, lightly bent path is a ruler laid through space. Small transverse forces leave measurable fingerprints when you look downstream. Our visitor, wrote a clean line on the sky before the conjunction. If 3 solar avalanches really crossed that line near the time of closest approach, the downstream line should kink. That is why the lack of a kink is not a shrug issue. It is the core tension that powers this investigation and sets up the next moves we will make with numbers and with images. When you strip away the glamour of a discovery and stare at the pixels, you meet the object as it really is. Hubble gave us that first sober meeting. The images showed a compact central brightness, wrapped in a soft veil, and a tail drawn away from the sunday. That is the signature of a body warming enough to shed gas and dust. It is not the bare, rocky glint of an inert shard. It is a living surface, responding to sunlight with a slow exhale that becomes a visible atmosphere in miniature. Size is the first question everyone asks, and the most slippery. Hubble does not resolve a 2 or 3 kilometer rock across interplanetary distances. Instead, astronomers model what the camera sees. They fit the shape of the blurred point, account for the hazy halo of the coma, and ask what size nucleus would reproduce that brightness if it reflected like a typical comet. This is why size comes with a quiet if. If the surface is dark, like most comets, the nucleus sits below roughly 3 kilometers across. If it is brighter than usual, the true body could be smaller. If it is darker still, a bit larger. The number is an anchor with honest slack in the rope. The shape of the light around the nucleus carries clues of its own. A round, symmetric glow close in and a tail that steadily thins suggests steady heating rather than violent outbursts. Subtle asymmetries hint at jets, the way a kettle hisses harder along one scene than another. With enough images over enough days, you can infer rotation as patterns in the coma drift and realign. Even in those early looks, the stranger behaved like a comet should. It made a halo. It cast a tail. It answered the sun with vapor and dust. Then the James Webb Space Telescope pointed its spectrometers and did what Hubble cannot. It separated the blended glow into a barcode of colors, each bar a fingerprint for a molecule. Water leaves a distinctive imprint. Carbon monoxide leaves another. Carbon dioxide is different again. The strongest lines in the data leaned hard toward carbon dioxide. Water was not absent, but the balance favored carbon dioxide in a way that is uncommon for comets born and raised around our sunday. That is not just trivia. Chemistry is biography written in light. What could put carbon dioxide in front? One path points to the cradle. If this body formed in a warmer zone of a different planetary system, water ice might have been scarce, while carbon dioxide ice remained stable. Another path points to weathering over great time. A traveler wandering between stars is bathed in cosmic rays and starlight for ages. The most fragile ices can be broken apart or lost, leaving behind species that are harder to remove. Either route leaves us with a nucleus that exhales a different cocktail when warmed. That cocktail shapes everything the sun touches. Chemistry steers the coma's behavior. Carbon dioxide releases at different temperatures than water and can drive activity farther from the sun than water alone. That shifts when the glow turns on, how it brightens, and how gas drag lifts dust to make the tail. It also changes the electrical personality of the cloud around the nucleus. Ionized carbon dioxide has different mass and charge than ionized water. Those differences matter when the solar wind flows through, because the wind does not push on neutral gas. It pushes on charged particles and the magnetic fields braided through them. Polarization and color trends in the coma add a whisper about the dust. Particles that are more carbon-rich or carry metallic grains scatter light differently than fluffy, icy clumps. Early hints suggested dust that was not wildly exotic, but not textbook bland either. That bolsters the idea that we are not just looking at a familiar comet in a new place. We are meeting a traveler with a long history, carrying a slightly different toolkit of ices and minerals, and that toolkit could influence how it handles both sunlight and the solar wind. Even the tail's geometry folds back into the story. A dust tail responds to radiation pressure and inertia. An ion tail responds to the solar wind and magnetic fields. In some frames, faint kinks and detachments appear in ion tails when the sun's wind snaps. That is a normal comet's way of showing the weather in space. If you see more compression than expected, or faster reorganizations near the time of any solar disturbance, you are starting to gather structure in the smoke. The kind of structure that turns hand-waving ideas about plasma into testable patterns. None of this crowns a new law of nature. It does something more useful. It narrows the credible options. A small nucleus under roughly 3 kilometers across, a coma and tail that behave like the product of steady heating, a spectrum with carbon dioxide out in front. dust grains with hints of character. Put together, the anatomy looks like a comet from elsewhere that has been aged and tuned by conditions unlike our own. The stranger is not unknowable, it is specific. And that specificity tightens the paradox we are chasing. If the nucleus is not a dense iron ball, and if the coma is active with carbon dioxide that ionizes readily, then any solar storm that crossed its path should have left fingerprints we could measure downstream. The telescopes gave us the bones and blood of the visitor. Now we have to see how those tissues respond when the star flexes, which is where the Mars checkpoint, the conjunction, and the triple blast enter the frame. Mars gave us a gift. In early October, the interstellar visitor threaded past the red planet at a range close enough for orbiters to try a look. Instruments meant for atmosphere sniffing and surface mapping turned to the moving speck and snapped it in context against familiar stars. When the images were measured against the predicted track, the match was crisp. The visitor was exactly where the math said it would be, moving exactly as fast as expected. That kind of cross-check is gold. It hardens confidence before the hard part begins. There is a reason navigators love waypoints. You want a solid fix before you sail behind a headland and lose the lighthouse. Mars was that fix. Ground observatories folded the Martian conformations into their orbit solutions. Error bars tightened. The ephemeris for the weeks ahead was posted and reposted. For a moment it felt almost easy. The plot was smooth. The numbers agreed. The timeline to closest approach to the sun looked clean and predictable. Then, geometry turned on us. From Earth, the path drew closer to the sun's glare each morning. The bright face swallowed the dim smudge. You cannot watch a moth in front of a stadium light with normal optics. The only way to keep eyes on the target was to switch to coronagraphs, instruments that slide an artificial eclipse over the solar disk so the surrounding region becomes visible. It is a clever trick with a hard truth attached. Those images are built for the sun's storms, not for faint dots that creep a few pixels per hour. Still, the handoff worked better than many dared hope. In the coronagraph frames, a tiny smear appeared, where the orbit said it should be. The cadence was not cinematic. A few frames per hour in the best sets, sometimes less. But across days, the motion connected. If the object had been deflected by outgassing in a surprising way, or if the pre-conjunction fit had been skewed, you would expect the smudge to wander from the predicted line. It did not. Confidence rose another notch, even as the view darkened into noise and scattered light. Coronagraph work forces a new kind of patience. The field is busy with expanding halos, streamer plumes, and cosmic ray flecks that masquerade as stars. You subtract backgrounds, you stack sequences, you trace a path that feels more like reading a watermark's signature than watching a bright lamp. The reward is continuity. Every frame that lands near the predicted position is another nail in the coffin of certain errors. Every frame also sharpens the stakes for what happens when the sun decides to flex. And it was flexing. Solar cycle 25 was marching upward. New active regions pinwheeled onto the far side and grew. Flares popped. Streamers kinked. Meteorologists of the sun were already busy with the Earth-facing weather. The far side is another story. We do not see it directly from here. We infer it from helioseismology and from spacecraft with different vantage points. During our visitor's conjunction window, whispers began to drift through the observing forums. There might have been not one coronal ejection on the hidden face, but a rapid sequence of them, and their geometry overlapped the predicted lane of the interstellar traveler. The emotional tone snapped from steady to electric. If those ejections were real, and if their expansion fronts crossed the right place at the right time, we had a natural experiment playing out behind the solar mask. A fast, small nucleus wrapped in a carbon dioxide forward coma would have met the most forceful plasma our star throws into space. The expected outcome is not theatrical destruction. It is modest momentum transfer that reveals itself later as a clean offset from the track laid down before conjunction. A few arc seconds at first, more with time, enough to show up when the object cleared the glare and returned to star fields we can measure precisely. This is where Mars mattered even more. The October cross-check gave us a reference with almost embarrassing clarity. With that in hand, post-conjunction positions would not be argued about. With hand waves, they would be compared to a path that had already survived serious scrutiny. Either the downstream line would kink, or it would not. Either the numbers would demand a new force in the ledger, or the story of missed hits and innocent geometry would carry the day. In the meantime, the coronagraphs kept whispering. The smudge stayed near the lane, even as the sun's background writhed. If a hit occurred, it was either too glancing to matter, or the effect was being soaked up somewhere other than the rocky heart. That is the thought that kept slipping back into focus. A coma is not nothing. Ionized gas and dust can carry currents and build magnetic pressure. In a close encounter with hot, tangled plasma, maybe the push spreads out and warms the cloud rather than shoving the core. By the time the object began to emerge from the glare, the community had split into two moods. One side was ready to plot offsets and call the shove small. The other side was ready to entertain. A different kind of interaction that converts impact into shape rather than motion. Both groups had the same plan. Get fresh astrometry. Compare against the pre-conjunction ephemeris. Let the sky speak. What started as a clean march of measurements had become a cliffhanger, framed by a planet on one end and a star on the other. Mars marked the trust we could place in the predictions. The sun hid the crucial moment when predictions faced the storm. Now we were about to find out whether our visitor's line would break, bend, or hold as if those explosions had been nothing more than luminous weather far away. Reconstruct the week when the sun grew teeth. The interstellar traveler slid behind the glare from Earth's point of view, and the star's hidden hemisphere began to stir. Far-side active regions swelled and twisted. Radio monitors heard the telltale hiss of turbulence in the solar wind. Helioseismology maps shaded in new patches of magnetic unrest. Then came the first eruption, then the second in quick pursuit, then a third that ballooned, like a ghostly halo, in skewed views from spacecraft that do not share Earth's line to the Sunday. 3 blows from the side we could not see directly. A coronal mass ejection is not a spotlight beam. It blossoms and expands like a slow-motion shock front, a 3-dimensional bubble whose shell thickens along some directions and thins along others. The source region sets the first aim, then the solar wind and surrounding structures shear and steer the cloud as it races outward. When observers say an ejection was directed toward a target, what they mean is that the expansion cone overlapped the target's predicted lane within the time it would take for the cloud to grow and cross that region of space. Our geometry was complicated and cruel. The traveler was near perihelion, roughly 1.35 astronomical units from the Sunday. From Earth, it was tucked into the bright skirt of the corona. From the Sun, it was off to the side, not grazing the photosphere, but moving through the inner heliosphere where the wind is young and the magnetic field is still knotted from its roots. Draw a line from a far-side active region, through the expanding cloud, and out toward that moving dot. If the timing works, the cloud and the coma meet. We lean on staggered vantage points to judge that timing. Spacecraft at different longitudes around the Sun catch the halo from an angle. A classical coronagraph near Earth sees the edge of the same event as a bright loop that swells and fades. Data analysts triangulate the front speed by following the same feature in multiple movies. You do not need perfect fidelity to get a window. Slow events take days to reach the traveler's distance. Fast events eat that gap in less than a day. A triple burst squeezes the odds that none of the fronts touch the lane. The far side matters because it is our blind spot. We lack a camera parked behind the sun to watch every flare and eruption head-on. We infer far-side activity from ripples that travel through the star, like sound through a drum, and from spacecraft that sit a bit to the side and see around the edge. That means timing is fuzzier, and trajectories are less certain. You can be fooled by projection. A halo can look symmetric when it is lopsided. You can be misled by a streamer that redirects a cloud while you blink. Honest caution is required, yet the overlap is tempting. The predicted positions of the traveler marched across the same longitudes the active regions occupied as they rotated toward us. The expansion arcs traced through those longitudes during the days that the smudge in coronagraph frames kept to its lane. Imagine standing behind a waterfall and watching a single leaf drift in front of the curtain. You cannot always say which sheet of water grazed the leaf. You can say the leaf survived the spray and kept its line. There is a second layer to the geometry, and it lives in the coma. The nucleus may be only a couple of kilometers across. The coma can stretch tens of thousands of kilometers, sometimes more, depending on activity. An ejection that misses the rock by a hair can still plow the cloud and rearrange the ion tail. That is why people began to comb through frames for subtle changes that track the passage of pressure waves. Compressed tail segments, ripples that run outward, brief disconnections that hint at magnetic reconnection. Each is a weather report, and together they map the timing better than a single dot on a star field can. The triple sequence sparks a natural question. Could three impacts from slightly different angles cancel the net push on the nucleus? In theory, yes, if the front struck at just the right times with opposed momentum components. In practice that demands a choreography, the sun does not often perform. It would be luck piled on luck, and nature rarely spends her luck that way. A more plausible reading is simpler. The fronts either missed the nucleus cleanly while manhandling the coma, or the forces were absorbed and redistributed in that diffuse envelope through currents and magnetic pressure. All of this funnels toward one decisive test. When the traveller re-emerged into darker sky, did precise astrometry show a kink in the downstream line? If yes, then at least one front delivered a measurable shove, and our task is to tally the magnitude and sign. If no, then either we witnessed a near miss 3 times in a row, or we met a cloud that can turn a punch into heat and shape without moving the core very much. The far side gave us drama. The geometry gives us a ruler. The next nights would tell us which story survives contact with the sky. A lot of space weather talk blends flares and coronal mass ejections into one fiery blur, so let us separate them. A solar flare is a flash of radiation. It is a burst of light and high-energy particles from magnetic knots snapping on the Sunday. It arrives fast at alpha, the speed of light, and it does not carry much push. A coronal mass ejection is different. It is matter. It is a billowing cloud of ionized gas, threaded with magnetic fields that truly leaves the sun and plows into space. Where a flare shouts, a coronal ejection shoves. Think of a coronal ejection as a slow-motion shock front. In the first hour, it swells from a tight arch near the sun into an expanding bubble with a bright rim. Inside the bubble, the plasma is hot and the magnetic field is tangled. Outside is the ordinary solar wind. The speed varies wildly. Some clouds lope along at a few hundred kilometers per second. The bruisers sprint at more than 2,000. The mass is large by human standards. Picture billions of tons of material, enough to fill a mountain valley if you could cool it and pour it like sand. Shove comes from 2 ingredients working together. The first is simple momentum. Even a small fraction of a billion tons moving hundreds of kilometers per second carries a slatch, a lot of oomph. The second is magnetic pressure, which is not a metaphor. A moving magnetic structure pushes and pulls on charged particles the way a spring pushes and pulls on a weight. A cometary coma is full of ions once sunlight strips electrons from gas. Those ions feel the grab of the passing structure. The result is a force spread over a huge volume that can compress, shear, and sometimes drag the inner cloud along. Now scale that picture down to the rocky heart. A typical cometary nucleus, only a couple of kilometers wide, might weigh a few trillion kilograms if it is fluffy and icy. If it is denser, it weighs more. If a coronal ejection's front sweeps across the nucleus directly and couples even a tiny fraction of its momentum, the nucleus should gain or lose a little speed. The change does not need to be dramatic to be visible later. A few meters per second is nothing to your car. It is everything to a precise orbit that threads millions of kilometers in the weeks after the tit. You can feel this without equations. Imagine standing on skates while a giant air mattress slides by and brushes your arms. You do not topple, but you drift a little in the mattress's direction. If 3 mattresses brush you from similar angles in quick succession, you will not end up where the rink map predicted. You will be off by a smooth, measurable amount. That is what astronomers expect when a nucleus in a hyperbolic hurry meets one or more dense fronts of magnetized plasma. We also know what a coronal ejection does to the coma and tail, because comets have served as windsocks for centuries of solar weather. Tails kink when pressure builds. Ion tails sometimes snap and reattach when the passing magnetic field reconnects. The coma brightens as it compresses, then relaxes as the front moves on. All of those are signatures of energy and force being deposited. None of them require the nucleus to be battered. They do require that something in the system felt a push. There is an important caveat. A coronal ejection is not a rigid wall. It is a frothy shell. Density and field strength vary within it. Filaments carry more mass and more tension. Cavities carry less. If the nucleus slips between the heavier filaments, the momentum transfer drops. If the ejection glances the outer coma rather than the inner core, the effect on the nucleus can be very small while the tail still thrashes like a windswept flag. So a miss is always on the table as an explanation. It is simply not the first one you reach for when multiple fronts overlap the path. What about the argument that a magnetized cloud might press on one side of the coma and then on the other, cancelling the push? Nature can do that if the timing cooperates. In practice, cancellation requires symmetry the sun rarely provides. Different fronts carry different speeds and internal wiring. They do not play neat rounds of tug-of-war that add to zero, so the default forecast is straightforward. If the fronts truly cross the path near the time of closest approach, the coma should have noticed and the nucleus should have shifted a little. The downstream test is to compare the post-conjunction sky positions against the pre-conjunction line. A clean growing offset says a shove landed. No offset says the fronts missed the core, or the forces were absorbed and redistributed in the ionized cloud in a way that left the rocky heart almost untouched. Either answer is valuable, but only one leaves the paradox standing at full height. Before we flirt with exotic ideas, we owe the ordinary ones a full hearing. Start with the cleanest. The front simply missed. A coronal ejection is not a rifle shot. It is a growing bubble with structure, a patchwork of denser filaments and thinner cavities. Our traveller is a pebble compared with that quilt. The nucleus spans only a few kilometers at most. The coma is bigger, yes, but still a small target in a vast and restless flow. If the dense parts of the first two fronts passed a bit high and the third slid a bit low, the nucleus could have sailed on, while the outer cloud felt some weather and then relaxed. Mist is not a cop-out, it is physics with a shrug. Yet the mist story has to clear two hurdles. The first is geometry. 3 fronts in a compressed window overlapped the predicted lane. Each had a fair cone of expansion. Space is large, but not infinite in this scene. The second is tail behavior. When a front grazes a coma, ion tails often kink and brighten. If the record near conjunction shows smooth, sleepy tails, the argument for a near miss grows stronger. If it shows compression waves or brief detachments that track the timing of the fronts, then the cloud noticed something, and the complete miss becomes harder to defend. Next comes the massive option. Maybe our size and mass assumptions are wrong by a big margin. We infer nucleus diameter from brightness and a guess at surface reflectivity. If the surface is darker than, we assumed, the nucleus could be larger and therefore heavier. If it is denser than a typical ice rock and more like compacted rock or even metal-rich, the mass rises again. A heavier object resists a given shove more. In the limit case, a dense planetary fragment with little porosity could shrug off fronts that would nudge a fluffy snowball. There is a catch in that slope. Change the albedo too far, and you contradict the coma brightness you already measured. Push the density too far and you must explain why a metal-rich boulder produces a lively carbon dioxide forward coma with a textbook morphology. You can thread that needle in principle. A layered rubble pile can hide a dense core under a more porous shell. Carbon dioxide can vent from heated carbonates, but each extra fold you add to the story is a cost. The more exceptions you need, the more you should ask whether you are saving a weak idea with cleverness. Now, for the romantic option among the ordinary ones. Maybe the pushes, cancelled. 3 fronts from slightly different directions arrive across a day or two. The first nudges left, the second nudges right, the third taps the brakes. The net change is small, and the downstream line looks clean. You can make a diagram that does this in an instant. The trouble is, the sun does not choreograph tidy symmetry on command. Each front carries its own internal wiring. They do not hit with equal speed or equal density. The coma is not a rigid ball. It is a breathing cloud whose currents and field alignments shift by the hour. You would be counting on a coincidence of timing, vector, and internal structure that is possible, but not likely 3 times in a row. There is a quieter variant that deserves attention. What if the fronts did not cancel each other, but the coma cancelled itself? Imagine pressure rising on the sunward side while currents close around the nucleus and spread the force across a wide volume. The inner cloud heats and compresses. The ion tail snaps and reforms. The energy goes somewhere. It just does not end up as a net push on the rocky heart. This is not magic. It is the difference between hitting a wall and hitting a springy net. You still deliver energy, but the net flexes and shares the load across many strands. The nucleus sits near the knot, moving less than your hand expects. Coronagraph limitations also belong in the ordinary bin. When you work near the sun, backgrounds are treacherous. Stray light, cosmic rays, and evolving streamers all try to fool you. A faint smudge can be measured a little high one day and a little low the next. Stack a few small measurement biases in just the wrong way, and a real offset could hide inside the noise. That is why post-conjunction astrometry under dark sky is the referee. If the downstream positions still hug the pre-conjunction line after the glare is gone, blaming coronagraph bias loses its punch. Add these strands together and you get an honest map. Mist is plausible if tail behavior stayed calm and timing argues against overlap. Massive is plausible within bounds, but it pays penalties in chemistry and coma style if pushed too far. Cancelled is the least satisfying because it demands a three-way coincidence from a messy star and a messy cloud. None of these are straw men. They are the first doors any careful team should try. If one opens, the mystery steps down a rung and we move on a little wiser. If none opens, we are left with a picture that keeps tugging at the edge of the frame. The sun's fronts did touch the cloud, and the cloud did what plasmas do. It bent, it conducted, it built pressure where fields tangled. It converted some of the storm's push into heat and shape rather than motion of the core. That is not a leap into fantasy. It is a gentle step toward a working hypothesis that we can test with tail morphology, with rotation inferences, and with the ruler of precise positions taken well after the glare. One more night of clean data can make the ordinary options sing or fall silent. That is why we chase the boring answers first and only then let the unusual theory through the door. If the visitor truly kept its line after 3 chances to be nudged, we will need more than shrug physics to explain why. Time to put a bold but testable idea on the table. A fast object wrapped in ionized gas is not just a rock in a headwind. It is a moving conductor threaded by the sun's magnetic field. Motion through a magnetic field builds electric fields. Electric fields drive currents. Currents reshape fields. In plasma, that feedback can grow teeth. What looks like a simple push becomes a conversation between the traveler and the star. If that conversation took place near perihelion, it could explain how the cloud took the brunt while the core stayed almost still. Start with what every active comet already does. Sunlight knocks electrons off molecules and dust. The solar wind sweeps those new ions downstream into a blast, the narrow ion tail that always points away from the sunday. Upstream of the nucleus, there is a bow shock, where the wind first meets the obstacle of the coma. Inside that shock, the wind is slowed and diverted. Pickup ions born in the coma get grabbed by the passing magnetic field and start to spiral, adding energy to the local soup. None of this is exotic. It is Comet Weather 101. Now adjust the dials for 3i Atlas. Higher speed through the inner heliosphere. A coma where carbon dioxide ions carry different mass and charge than water ions. A geometry that tightens field lines and flow patterns near closest approach. Currents try to close on themselves. Where the ion tail pinches, where the bow region ripples, you can build channels of flow that thread the coma like wires in fog. Magnetic pressure builds wherever those currents bend field lines. Pressure in a magnetic field is not a metaphor. It is a real force that pushes back, just as a compressed spring pushes back. If a coronal ejection arrives as a tangled magnetic structure, the encounter is not a wall slamming a pebble. It is 2 elastic webs, touching and deforming each other. The energy has to go somewhere. Some becomes heat. Some becomes compression. Some becomes reconfiguration of the tail as its field lines disconnect and reconnect. The net on the nucleus can be small, even when the local violence is large. This opens a second door many viewers do not expect. The coma might not only absorb, it might also nudge the star. If the coronal field above an active region is already stressed, a moving conductor that perturbs the nearby field could help tip a metastable system over the edge. Imagine a tight knot of magnetic threads ready to snap. A gentle pluck at the right spot triggers the release. That does not require the visitor to power the ejection. The sun supplies the energy. The visitor supplies the timing. In that picture, the ejection tends to launch toward the disturbance because that is where the knot loosened, which happens to line up with the traveler. Cause and aim become entwined. None of this flies unless it makes predictions. A coupling scenario should leave fingerprints in the shape and timing of the tails. Near the suspected encounters, the ion tail should show compression waves that march outward at the right speeds. Disconnections should appear and heal quickly. The coma should brighten modestly, then relax. Rotation signatures in the inner glow could damp or spike as current systems rearrange. Downstream, the orbit should remain close to the pre-conjunction line, with only small shifts consistent with ordinary outgassing. On the solar side, active regions that produce the ejections should rotate into view 2 weeks later, still looking gnarly, with loops and delta spots that speak of stored tension and recent release. There are hard edges too. If the nucleus carried a strong internal magnetic field, you would expect clear signatures in polarization of scattered light, and perhaps in radio scintillation if the tail crosses bright radio sources. If the coma conductivity must be high to share forces, then dust and gas ratios should support that with line strengths that show abundant ions. If the coupling was strong enough to drive ejections regularly, we would expect repeatable timing links between the traveler's position and far-side outbursts that survive careful statistics. Any of these missing pieces can kill the idea quickly. The romance here is not that we found a cheat code. The romance is that physics already in the book may be operating in a limit we rarely get to watch. A small, swift carbon dioxide-rich traveler presents just the right cross-section for currents to form and spread. A sun near maximum offers plenty of stressed regions ready to pop. Together they can manufacture a story where plasma takes the punch and the rock coasts on. We do not need to invoke intent or technology. We need to measure the deforming web as it flexes. So we now hold a working hypothesis. The visitor's cloud acted as an induced magnetosphere. It redistributed forces from passing coronal structures, turning push into heat and shape while leaving the nucleus nearly untouched. Its passage also may have nudged a loaded coronal knot into release, which made the ejections appear aimed at it. High drama, low mystery. The next parts are simple in design and hard in execution. Map the tail's ripples. Track the post-conjunction line with ruthless precision. Watch the active regions as they rotate into view. If the fingerprints are missing, we retire the theory. If they are present, we fold a new chapter of comet weather into the playbook and move on with a clearer map. Step into the cloud that makes a comet look alive. The coma is not fog in the everyday sense. It is a factory where sunlight splits molecules, charges build, and invisible forces tie gas and dust together into a single, twitchy organism. Neutral particles stream off the warm surface and drift a little way as ordinary vapor. Ultraviolet light from the sun knocks electrons loose. The solar wind adds its own ionizing punch. In minutes, a large fraction of that neutral breath becomes a charged plasma. Now, the rules change. Charged particles cannot ignore magnetic fields. They spiral, drift, and get swept into orderly chaos along field lines that thread the inner solar system. Picture a slow snow globe where every flake carries a tiny magnet, and the air is a stream you cannot see. Upstream of the nucleus, the solar wind meets the growing obstacle of the plasma cloud and slows. That slowdown makes a bow shock. Inside the shock, pressure stacks up and the wind diverts around the obstacle. The obstacle is not a steel ball. It is a springy mesh that yields where forces concentrate and stiffens where currents close. Currents do form. Any place you have a gradient in magnetic field or a shear between flows, charges separate a bit and then try to reunite by taking the shortest path through the plasma. Those paths stitch the coma into loops and filaments. Where the current bends a magnetic field, magnetic pressure rises. Magnetic pressure acts like a real cushion. Push on it, and it pushes back. The stiffer the field, the firmer the cushion. The denser or more conductive the coma, the more easily it can carry the current that builds that stiffness. 3 features of a carbon dioxide-heavy coma matter here. First, carbon dioxide begins to drive activity farther from the sun than water alone. That means the plasma factory is up and running well before perihelion and remains lively even as distance grows. Second, the ions are heavier than many hydrogen-rich species. Heavier ions gyrate with wider loops and store more momentum during each turn. Third, carbon-rich dust can carry charges well, so the dust and gas together build a more coherent medium for current to flow. You do not need a lab to test these exact values on this exact object. You only need to see that the dials all point in the same direction. More charge, more structure, more magnetic pressure where flows squeeze. Now bring in a coronal ejection. Its leading edge is a wall of compressed plasma, tied to a twisted magnetic field. As the wall hits the coma, the outer layers feel a surge in pressure. Currents spike, field lines bend. The bow region thickens and the ion tail narrows. Some energy becomes heat. Some becomes waves that run down the tail like ripples on a flagpole rope. The The nucleus sits near the center of this flexing net. The forces on opposite sides rarely match perfectly, but they can nearly balance when spread across a wide, conducting volume. The end result can be a loud show in the tail and only a whisper in the motion of the core. There are signatures to hunt. Compression should brighten the coma slightly and push the ion tail into a sharper, straighter lance. Minutes to hours later, the tail can show kinks that travel outward at speeds set by the local wind and field. In strong events, the ion tail can disconnect, a clean break that reforms quickly as lines reconnect. Dust tails answer more slowly because dust is heavier and feels light pressure rather than magnetic force. If you see ion features dance while the dust tail barely nods, you are looking at magnetism taking the lead. Rotation of the nucleus can modulate all of this. Jets on the surface vent in patterns as the sunlit hemisphere turns. That paints spiral textures in the inner coma that beat like a clock. A storm that arrives can damp that clock as compression smooths the flow, or it can accent the spiral as a jet couples more strongly to the pinched field. Watching that rhythm speed up, fade, or snap back tells you how the inner coma reconfigures its currents under stress. The most counterintuitive piece is also the most important. A system can absorb large energy without moving its center much when the energy goes into modes other than bulk translation. Heat is one mode, compression is another. Magnetic tension stores energy like a wound spring. The coma has all three. If you insist on thinking of an impact as a bat hitting a ball, you will miss what a web does when a gust hits it. A web flexes, it hisses with motion, it leaves the spider roughly where it started. None of this denies momentum conservation. It teaches where the momentum went, into swirling ions that later shed their energy down the tail, into field lines that snap and rejoin, into subtle reflows that undo part of an earlier push. When you add those pieces, the nucleus can emerge with only a tiny change in speed, even though the local weather was ferocious. That is the magnetic cushion in action, so when the coronagraph frames show a calm smudge where a kink might have been, do not mistake calm for quiet. The cushion could have done its job. The real test is whether tails whispered the story while the core stayed steady. Those whispers are the map we need to decide if the cloud truly turned a storm into shape rather than shove. A bold idea only earns airtime if it points to things we can actually check. Electromagnetic cushioning sounds neat. It lives or dies by fingerprints in the sky and on the Sunday. So, we set traps. We write down what must be true if the coma acted like a magnetic cushion and if the visitor nudged a loaded solar knot into release. Then we walk those traps in order. If they stay empty, the idea falls. If they spring shut, the story gets teeth. First trap sits in the tail. Compression waves should march down the ion tail at plausible solar wind speeds in the hours after each suspected encounter. Not a vague brightening. A wave that starts near the coma, sharpens the tail into a lance, then glides outward while fading. Ion tails answer the wind and field. Dust tails answer sunlight and inertia. If the ion tail dances, while the dust tail barely nods, magnetism led the scene. If both tails act the same, we are likely watching ordinary brightness flicker rather than structured compression. Second trap lives in timing. The wavefront positions along the tail should line up with a timeline that matches the ejection launch and travel. A slow ejection means late waves, a fast one means early waves. When you plot distance along the tail against time, you should get a slope that matches a reasonable local wind speed. If nothing lines up, the cushion story leaks. If it does line up, we gain a clock that ties the sun's punch to the cloud's response. Third trap watches the inner glow. The coma near the nucleus should brighten modestly during a compression and relax after. Rotation signatures painted by jets should show temporary damping or a short-lived accent as currents rethread. You can track that by looking for repeatable patterns that pause, smudge, and then resume. A clean pause speaks to pressure making order. A random jitter says background noise. This is subtle work, but it is where the physics becomes local rather than theatrical. Fourth trap sits on the orbital ruler. Post-conjunction positions under dark sky must hug the pre-conjunction ephemeris within small, consistent drifts that are explainable by normal outgassing. A growing, one-way offset says a shove landed on the nucleus. A random walk says, measurements are sloppy. A tight line says the core barely moved. If the line is tight, the cushion idea survives the hardest test. If the line is kinked, the idea pays a tax. We then measure the kink, and ask whether 3 small glancing hits can account for it without invoking anything fancy. Fifth trap turns to the Sunday. The active regions that birthed the suspected ejections should rotate into view roughly 2 weeks later, looking worked over. Loops should be complex. Magnetograms should reveal tangled polarities and delta spots that scream stored tension and recent release. If the regions roll around the limb looking mild and forgettable, the claim that they launched large ejections grows weak. If they look gnarly and remain productive on the Earth facing side, a loaded state before the visitor's passage becomes far more plausible. Sixth trap reaches for radio and polarization. If strong currents threaded the coma, fine dust grains can align or at least scatter light in telltale ways. Polarization angle and depth can change during compression and then relax. If the tail crosses bright background radio sources, tiny flickers in signal can betray a roiling plasma sheet. These are demanding measurements, but they sharpen the line between quiet cloud and current-carrying mesh. Seventh trap is statistical. If coupling is real, alignments between the visitor's position and far-side outbursts should not only happen once, they should cluster more than chance predicts during the window of strongest interaction. You do not decide this by memory. You log times. You run the null model. If the pattern vanishes into chance when counted with discipline, the idea loses air. If a signal remains after the math, the conversation with the sun starts to look like more than coincidence. There is also an escape hatch to close. A powerful jet could mimic a small shove by thrusting unevenly during conjunction and then calming later. That would leave a one-sided offset without solar drama. The fix is to track rotation-linked variations in brightness and direction of the inner tail before and after conjunction. If the outgassing thrust changed character right when the offset appeared, the jet story gains ground. If jets look steady while positions hold, the solar side of the ledger keeps weight. None of these traps require belief. They require patience, coordination, and clean reductions. Coronagraph movies to set launch times. Ground-based astrometry under dark sky to measure the line. Narrowband images that isolate the ion tail so waves stand out. Polarimetry for the dust story. Magnetograms and flare logs for the returning active regions. Each piece can be wrong alone. Together, they either tell one story or they do not. This is how we keep wonder honest. We do not scold the daring idea. We make it earn rent. If tails whisper in sequence, if regions roll into sight looking spent, if the orbit stays tight as a drum, then the cushion holds. If the whispers fail and the line kinks, the shove wins. Either way, we learn something we did not know last month. That is the prize we chase. To understand a newcomer, you look at the family it might belong to. In our case, the family is tiny. 2 earlier interstellar passers-by set the stage before 3i Atlas ever brushed our sunlight. One was a riddle with polished edges, the other was comfortingly normal. Together, they sketched the ends of a spectrum. Our traveller threads the middle with a look we recognize and behaviors that keep us leaning in. Begin with the first messenger. Oumuamua arrived in 2017 like a silent knife, small and faint, and already outbound when we noticed. The orbit said Interstellar, and the light curve said weird. It brightened and dimmed in a rhythm that fit a long, thin shape or a flat, wide one flipping end over end. There was no obvious coma, no fuzzy halo of gas, no tail to point away from the Sunday. Yet as it left, its motion drifted from the path gravity alone would draw. A small, steady acceleration appeared, the kind comets get from outgassing jets, but without the usual vapor signature. That paradox launched years of explanations. Maybe hydrogen ice boiled invisibly. Maybe nitrogen frost sloughed off. Maybe a skin of dust and pebbles released gases too subtle to see. Whatever the mechanism, the lesson stood. Interstellar is a permission slip for strange. Then came Borisov in 2019, discovered by an amateur with a homemade telescope. Where Oumuamua was a puzzle box, Borisov was a deep breath. It looked like a textbook comet, bright coma, obvious tail, spectra with familiar molecules. It still traced a hyperbola and kept a permanent ticket out of the solar system, but it behaved in ways that felt comfortably known. If you were writing a bestiary, you would put Oumuamua at one edge, a sleek outlier with hidden thrusters, and Borisov at the other. The archetype that tells you alien nurseries can make cousins of our local comets. Now place 3i Atlas on that map. Hubble shows a compact nucleus wrapped in a classical coma, with a tail driven by sunlight and the solar wind. That rhymes with Borisov, not Oumuamua. But the chemistry leans hard on carbon dioxide, which is uncommon for our homegrown comets. That tips the head toward Oumuamua's lesson that composition and behaviour can ignore our expectations. The size estimate, under roughly 3 kilometers across, makes it larger than Oumuamua's likely 100-meter scale and comparable to, or bigger than, Borisov's core. The speed near 60 kilometers per second at infinity is brisker than both earlier visitors. That extra speed means less time near the sun and less room for forces to accumulate, which sharpens the stakes of any claimed shove or lack of one. Activity patterns also matter. Oumuamua showed none we could see, yet drifted. Borisov outgassed generously and acted as predicted. 3I Atlas breathes, glows, and carries a live ion tail, but if its post-conjunction path hugs the pre-conjunction ephemeris, it will have done so while ignoring the kind of shove a cluster of coronal ejections might deliver. That combination is new. An active coma with chemistry that promotes strong ion behavior, living through loud solar weather and still keeping a clean line, would demand we add a page to the comet weather chapter rather than a footnote. Why compare at all? Because patterns are how we turn anecdotes into knowledge. With only one case, you tell a story. With 2 cases, you draw a line. With 3, you start to see a plane where properties vary together: shape and size, chemistry and activity, distance, tail temperament under stress, sensitivity to small forces during fast flybys. Each visitor plants a stake in that plane. Oumuamua says a small dry surface can still drift. Borisov says an active, water-friendly comet can play by the book. 3I Atlas says a carbon dioxide forward traveller can light up early, stay lively near perihelion, and, if our measurements hold, leave strangely little dynamical trace after the sun throws a fit. There is a deeper current here. Interstellar diversity is not a surprise. It is the default. Planetary systems form under different elemental balances. They shuffle worlds, smash them, bake them, and freeze them at different times and places. Ejecta inherit those histories. A shard from an inner warmer zone keeps different ices than a husk from the deep freeze. A body aged for eons between stars accumulates scars and loses volatiles in a way a young comet never has time to do. That is why a carbon dioxide dominant coma is not just a label. It is a clue to a life story that unfolded under another sun. And yet comparison also sobers us. The urge to declare a revolution is strong, especially when a paradox glows on screen. Oumuamua taught restraint by being both unearthly and likely natural. Borisov taught humility by being gloriously ordinary after all the hype. 3I Atlas will teach one of those lessons again. If post-conjunction astrometry shows a kink, we will weigh shoves and near misses. If the line stays tight while tails show compression and disconnections in step with distant eruptions, the coupling page gets written in careful ink. So the company we keep is small but loud. Each member bends our categories. Together they force us to write a broader field guide for visitors from beyond. The next one will arrive sooner than you think, as surveys sharpen. When it does, these 3 stories will be the legends we use to decide what to point where, which instruments matter first, and how to keep our minds open without letting our guard down. 3 stakes make a tripod. Set them well, and the next camera shot is steady. Half the star we live with is always turned away. That simple geometry is our biggest weakness during an active cycle. Eruptions brew on the hidden face, and we only see their consequences as ripples in the solar wind or as tilted halos in off-angle spacecraft. To make a map of a place we cannot see, we listen. The sun rings like a vast drum. Waves travel through its body and return to the surface with tiny timing shifts that betray hot magnetic knots on the far side. Helioseismology converts those shifts into patches on a globe, a weather chart for a hemisphere we cannot photograph. The map is never perfect. The patches are fuzzy, their borders soft, their strength estimates uncertain. But when a big region grows, the drumbeat changes enough to warn us. That warning matters because the sun rotates. At the equator, an active region takes about 4 weeks to circle, back into view as seen from Earth. Near the poles, the spin slows. Differential rotation stretches and shears magnetic fields, feeding the very storms we care about. So a region that erupts on the far side today can roll into direct view 2 weeks later, still hot with tension, a rotating threat that now faces Earth. Spacecraft give us slanted eyes around the limb. A platform slightly ahead or behind Earth in its orbit can catch the edge of a far-side eruption as a side-lit halo. Coronagraphs near Earth see the same event as a ghostly ring that brightens and fades. Put those hints together with the drum map, and you have a timeline. A flare pops, a coronal ejection blooms. The expansion front leaves at a few hundred to a few thousand kilometers per second. Hours to days later, the inner heliosphere responds. If a traveler near perihelion sits along that lane, the front and the coma can meet. Weeks later, the culprit region spins into view with scars. Active regions have personalities. Simple ones look like clean pairs of sunspots. Complex ones twist into tangled multipoles with mixed polarities jammed together. Magnetograms paint those fields in stark black and white, and forecasters learn to read the patterns the way meteorologists read pressure lines on a storm map. Delta spots are a red flag. They signal strong fields packed into small spaces, the kind that store and release energy in sudden bursts. During a rising cycle, such regions multiply. The far side becomes a factory you can hear but not see, and your job is to decide which products will arrive at our side in 2 weeks. That rotation provides a built-in test for the triple blast story. If far-side regions launch 3 strong ejections during conjunction, we should expect at least one of those regions to roll into sight, looking worked over, yet still potent. Loops, arcing high. Penumbrae shredded into filaments, flare rates elevated for days. If instead the limb reveals quiet decaying freckles, the case, for major far-side explosions, weakens. This is not perfect logic. Regions can relax after a binge. They can erupt their guts out and then go dull. But population-level behavior helps. When multiple signals line up, confidence rises. Understanding the far side also resets expectations about coincidence. During solar maximum, clusters of regions span wide longitudes. Eruptions often occur in flurries. If you draw a straight line from any point near the Sun through the inner heliosphere, odds are decent that some expansion front will cross it within a few days. That is not conspiracy. It is seasonality. The hidden hemisphere is loud more often, so alignments stack up without meaning. The task is to separate casual overlap from events that share timing and geometry too neatly for luck. Our blind spot is shrinking, but not gone. A dedicated observer trailing or leading Earth by a quarter orbit would transform far-side watching. Until then, we live with proxies. We lean on the drum map, the limb halos, the way streamer belts twitch, and the return of scarred active regions. The method is messy, but the rhythms are real. The Sun is not random noise. It breathes in cycles and sings in modes, and those patterns let us place windows on the calendar when unusual alignments are more likely. All of this feeds back into the traveler's tale. If you think the triple front scenario is plausible, you should see the returning regions snap into the frame like culprits entering a lineup. If you think near misses, explain everything. You still expect the lineup to hold faces that could have thrown the punches. Either way, the far side song sets the beat for our test. A region advances. The drum grows louder. Cameras catch the limb. A halo blooms. Days later, tails should stiffen and ripple. Weeks later, spots walk onto the stage and we read their scars. The deeper lesson is humbling and useful. We will always have blind spots. The fix is not perfect vision, but better inference and faster follow-up. The far side taught us to listen to a star and to think in rotating frames, to treat tomorrow's space weather as a moving target we can stalk. That practice makes us better at everything from protecting satellites to catching the next interstellar visitor in the act. The Sun keeps half its face hidden. We have learned to meet that secrecy with patience and geometry. Good science begins with what is on the table, not what we wish were there. On the table, we have discovery circulars with positions tied to star catalogues. We have Hubble images that resolve a nucleus wrapped in a coma. We have spectra that lean hard on carbon dioxide. We have Mars-side conformations that pinned the orbit before the object slipped into glare. We have coronagraph frames where a faint smudge tracks the posted ephemeris while the Sun throws luminous weather across the field. That pile is not gossip. It is the backbone that holds the story upright. What we want is sharper and fussier. We want high-cadence coronagraph sequences, calibrated for faint moving targets rather than tuned only for coronal loops. We want raw spacecraft logs that trace plasma density and magnetic field direction in regions the expansion fronts actually crossed. We want precise post-conjunction astrometry over many nights from dark sky observatories so small offsets cannot hide inside jitter. We want magnetograms of the returning active regions with enough resolution to read tangled polarities like handwriting on a chalkboard. Desire is not a plan, so we map how to turn wants into data. Start with coronagraphs. These cameras are built to watch the sun breathe, not to chase faint pebbles crawling a pixel at a time. Background subtraction must tame scattered light and streamer drift. Cosmic ray hits need forensic cleaning. Frame registration has to be perfect, or a real smudge becomes a smear. Teams who do this well publish their methods and their residuals. When they say the smudge followed the line, they also show how they know the line is not an artifact of the cleaning. The standard is neither easy nor glamorous, it is essential. Now, the orbit work, astrometry is a craft that rewards boredom. Measure the stars, fit the plate, log the wind, repeat. When a target emerges from glare, the temptation is to celebrate a single, clean night. Resist that urge. What matters is a time series long enough that micro-errors average down. What matters is diversity in sights and instruments so one camera's bias does not steer the answer. Post-conjunction nights should carry the weight, because only they can tell you whether a shove landed during the days when the object was next to the sun, and most of us were blind. In situ plasma data would be a gift. Spacecraft far from Earth taste the wind directly. They feel when density spikes and when the magnetic field swings. Those data often live behind brief embargoes while teams validate and prepare papers. That is normal. It is also frustrating when a public conversation is running hot. The antidote is patience and clear expectations. You note that a measurement exists. You accept that it will land when it is vetted. You do not fill the gap with wishful curves. Peer review is not a magic stamp. It is a process that forces claims to survive hostile reading. Preprints are not a sin. They are how communities move quickly, but they carry a debt. Authors must show their work and accept that revisions will follow. The public can help if it behaves like a lab group rather than a rumour mill. Share calibrations, not just screenshots. Share scripts that reproduce plots. Share failures that explain why a tempting signal collapsed when the method tightened. The fastest way to the truth is a crowd that values being right over being first. Citizen science belongs here with pride and with guardrails. Amateurs with excellent gear and discipline can measure positions to remarkable precision. They can collect narrowband images that make ion tails pop. They can monitor night after night when big facilities are overbooked. The guardrails are simple: publish uncertainties, share raw frames. Accept that a faint detection near the sun is provisional until others replicate it. That humility does not dim the achievement, it brightens it. What about the whispers that the sun launched 3 monsters aimed down the line? Eruptions did happen. The far side was busy during that window. Whether the expansion fronts actually crossed the lane is a geometric question that honest analysts can disagree about until more angles arrive. The right move is to tie each claimed launch to times, speeds, and directions with ranges and error bars, then ask the tails and the downstream positions to answer yes or no. The wrong move is to let the drama outrun the ledger. There is also a soft bias that creeps in whenever a story glows. If you expect deflection, you will squint until a kink appears. If you expect invulnerability, you will wave away small offsets as noise. The cure is pre-commitment. Before you look, write down what change would count as real and what would not. Write down how many nights you need before you call it. Then keep your own promise. We end where we began. The evidence we have is strong enough to pose a paradox. A lively carbon dioxide forward traveller crossed a stormy inner heliosphere and so far looks on track. The evidence we want is within reach if we measure deliberately and share well. When the next batch lands, the paradox will either fade into a tidy nudge or sharpen into a lesson about how plasma can turn, push into shape. Either way, the path from want to have will have done its job and left us smarter than we were. There is a new kind of apprentice in the observatory. It does not yawn, it does not blink, and it never gets bored of looking at one more noisy frame near the Sunday. Artificial intelligence joined the hunt because modern telescopes drown us in images. Most frames are quiet. A few hide the thing we care about. The trick is sorting them fast without missing the faint smudge that matters. When the field is a snowstorm of stray light, cosmic ray freckles, and boiling streamers, software becomes a partner that does not flinch. Start with the coronagraph problem. A faint visitor creeps a few pixels per hour. while the background writhes. A human can blink frames and hope the eye catches motion. A machine can align the field to sub-pixel precision, learn the heartbeat of the background, and subtract it away. Convolutional models, trained on years of coronal movies, learn what a streamer looks like when it sways, and what a cosmic ray looks like when it stings the detector for a single frame. What remains is a short list of moving candidates. The smudge that reappears with consistent speed and direction climbs to the top. Sequence matters as much as snapshots. The model does not only ask whether a dot is present, it asks whether a path exists. Linking low, confidence detections across time is a job for trackers that expect near-constant velocity and gentle curvature. Think of a soft version of a detective string on a wall, connecting points that make sense together while ignoring bait that does not. Add optical flow methods that map how features drift between frames and you get a motion field. Subtract the motion the sun owns and the leftover motion belongs to the traveller. Now flip to the solar side. Coronal mass ejections are not identical. Some are fast, some are ragged, some hide behind projection tricks that make a lopsided bloom look like a symmetric halo. Machine learning shines when it sees thousands of examples and learns the difference. A model can watch the first 30 minutes of a bloom and estimate its speed and likely spread. It can fuse views from different spacecraft into a single three-dimensional front. It can hand that front to simple propagation rules that guess when and where the front will cross a given lane. In space, none of this replaces physics. It accelerates the first pass so people can spend time on the cases that matter. Orbit fitting gains speed here too. Classic solvers chew on positions and update a best path with every new night. Wrap that in a filter that expects small drifts and penalizes wild jumps, and you get a live estimate that tightens in real time. Feed the filter not just ground-based astrometry, but also coronagraph positions with honest uncertainties, and it will weight them appropriately. If a shove happened, the filter will begin to pull away from the pre-conjunction line in a smooth, testable way. If the line does not budge, the filter will say that too, and it will publish how sure it is. A machine can also stage a rehearsal of the week we care about. Build a population of virtual visitors with slightly different sizes, reflectivities, and outgassing habits. Paint a set of virtual ejections with speeds and directions that match the bounds we measured from the Sunday. Let the cloud and the traveller meet in thousands of combinations. Count how often a measurable offset appears downstream. If the answer is almost always, then a tight real orbit is a louder message. If the answer is rarely, then the lack of a kink is unremarkable. You do not need to guess. You can test the odds. There are traps. Models learn what you feed them. If every training comet is from our backyard, the model will ignore interstellar quirks. If the dataset is thin on far-side eruptions, the model will be overconfident in the wrong places. Cosmic rays do not look like stars until the night the detector behaves differently, and they suddenly do. The cure is humility in the output and diversity in the input. Mix simulated scenes with real ones. Randomize brightness, smear, and noise. Force the model to cope with the ugliness we actually see, not the neatness we wish for. Most important, the machine must show its work. Scores without reasons are not helpful. We want saliency, maps that highlight which pixels drove the call. We want residuals that reveal what the subtraction left behind. We want uncertainty alongside every number, so a human can decide whether tonight's point bends the line or sits inside the fog. When the tool behaves like a colleague who explains, trust grows. This is not a story where code replaces curiosity. It is a story where code makes curiosity scale. The field near the sun is hard, the nights are short, the windows are few. A tireless apprentice can sift the glare, flag the ripples in the ion tail, estimate the vigor of the coronal bloom, and keep the orbit fit honest while we sleep. Then we wake, check the trails it left, and push the next question forward. If a cushion turned push into shape, the patterns are there. If a shove landed, the line will bend. Either way, the machines will help us see it faster and argue about it with better evidence. It is tempting to treat all of this like a cosmic soap opera, a mysterious visitor, a temperamental star, beautiful images and strange chemistry. But the stakes are not only aesthetic. Coronal mass ejections are not fireworks, they are weather with teeth. When the fronts that miss a tiny nucleus do not miss Earth, our technology feels it. The same physics we are dissecting to explain a clean orbit explains why your navigation app can drift, why your flight is rerouted. why a transformer hums in the dark and then goes quiet. Start with the shell above our heads. Satellites sit in a sea of charged particles. During a strong solar storm, that sea thickens and swirls. Drag rises on low orbiters, altering their paths and shortening lifetimes. Radiation doses spike for spacecraft in high orbits. Electronics face single-event upsets, bit flips that can crash a system or corrupt a data stream. Engineers harden hardware and build in redundancy, but storms still leave scars. If we understand how magnetic structures couple to plasma around small bodies, we sharpen the same magnetohydrodynamic models used to forecast when satellites should hunker down and when operators should switch to safe modes. Navigation depends on timing. Global positioning signals traverse the ionosphere, the thin shell of charged gas that blankets Earth. A storm stirs that shell, changing how signals bend and delay. Your position solution wobbles. For surveyors and precision agriculture, that matters. For landing aircraft in poor visibility, that matters even more. Better forecasts of ionospheric turbulence come from better maps of how solar fronts carry magnetic tension and deposit energy. That is why a traveller's ion tail is not just a pretty ribbon. It is a laboratory for the same coupling that perturbs the air above our heads. Power grids are the quiet giants at risk. Long wires act like antennas for slow changes in geomagnetic fields. During a severe storm, currents are induced in transmission lines and can saturate transformers. Heat builds, protection schemes trip, blackouts ripple. Modern grids are smarter than the ones that suffered decades ago, but the hazard remains. When a forecast says a front is coming with a south-pointing magnetic field, grid operators can reroute flows, reduce loading, and watch vulnerable nodes. Small improvements in the way we predict the orientation and strength of incoming fields translate into real decisions that keep lights on. Aviation feels the weather too. Flights that arc over polar regions enjoy shorter routes, but during storms, the high-latitude radio links they rely on can fade. Cosmic radiation doses tick up for crew and passengers at altitude. Airlines reroute to lower latitudes or lower altitudes, burning more fuel and altering schedules. A solar event that might seem abstract on a screen becomes a spreadsheet of delays and costs. Space weather agencies brief airlines daily. Any improvement in lead time or confidence helps. Farther out, human exploration folds the same physics into life support. Astronauts on a station, or on a path to the moon, need storm shelters ready when solar energetic particles surge. The warning is not an optional nicety. It is the difference between a manageable dose and a mission threat. Robotic explorers around Mars and elsewhere feel the same winds our visitor felt. Their data teach us which fronts are fluffy and which carry sharp shocks. Our interstellar traveller's clean line under stress, if confirmed, will refine how we estimate momentum transfer and field topology in those fronts. The lesson propagates from a tiny rock to the safety margin of a crew. Pipelines, rail signaling, even well logging, and survey equipment can suffer when geomagnetic variations grow. These effects are not daily news because engineers build guardrails, but the guardrails lean on models. Models lean on measurements. Measurements live where physics and geometry meet. That is why we keep circling back to tails, to comas, to the way a moving conductor distributes forces. The more we learn about that dance, the more honest and useful our space weather playbooks become. There is a civic angle too. Auroras are the charming face of storms. They lure people outside with cameras and wonder. It helps to pair that joy with literacy. Know that a forecast with moderate confidence means lights in the sky for some and static for others. Know that an outage during a storm might be a protective trip, not a fragile grid failing. Know that a delayed flight over the pole is a safety call, not an inconvenience invented at random. Curiosity that understands trade-offs makes us better citizens of a planet tethered to a variable star. So, when we obsess over whether a carbon dioxide-rich coma absorbed a punch, do not mistake the motive. We are not looking for excuses to turn every comet into a legend. We are looking for leverage. If a small body can tell us how magnetic pressure redistributes momentum, it can help us predict when a shell of plasma will push hardest on our own magnetosphere. If an ion tail can record a passing shock down to the minute, it can help us time the same shock at Earth with tighter confidence. Knowledge that starts in romance ends in readiness. In that sense, 3i Atlas is not a distraction from practical concerns. It is a test case at the edge of what our models can handle. If the orbit stays clean while the tails dance in step with distant eruptions, we add a page about magnetic cushioning that improves forecasts. If the line kinks, we sharpen our sense of how often near misses masquerade as mysteries. Either way, the next alert that crosses a dispatcher's desk will carry a little more truth. That is why any of this matters. Chemistry is biography written in light. When the James Webb Space Telescope teased out the spectral lines from 3I Atlas, the strongest bars belonged to carbon dioxide. Water was present, but the balance tipped the other way from what we see in many homegrown comets. That single tilt changes the backstory. It hints at a nursery where temperatures, pressures, and elemental ratios did not mirror our own. It also connects our visitor to a wider revolution that Webb has been driving in exoplanet atmospheres, where carbon dioxide keeps showing up in places our old models did not predict. Start with the basics. Ices are picky about temperature. Water ice hangs on in the outer cold of a protoplanetary disk. Carbon dioxide can remain solid a bit closer in. Carbon monoxide clings on farther out. Where a small body forms, and how quickly it is moved around by giant planets, sets the inventory it carries for the rest of time. If 3I Atlas was assembled in a zone that was warm enough to deplete free water but still cool enough to lock in carbon dioxide, you would expect exactly what we see now that sunlight warms it. The first breath is carbon-driven. Water joins in, but it is not the lead singer. There is another path to the same outcome. Time is a chemist. An object, wandering between stars for billions of years, absorbs cosmic rays and ultraviolet photons. Fragile ices break apart and escape. More robust species remain. The surface devolatilizes layer by layer. A visitor that was once water-rich could age into a body where carbon dioxide carries the show. Either origin gives you a coma that ionizes into a plasma with different mass and charge than the water-heavy mix we know best. That matters for tails and for any magnetic cushion the coma might form when solar weather hits. Exoplanet results amplify this line of thought. Webb has watched starlight filter through alien skies and found atmospheres where carbon dioxide dominates far more than our old recipes expected. Some Neptune-sized worlds in temperate zones show carbon-rich mixes with little water vapor in the bands we can see. The message is not that those planets look like comets. The message is that chemistry across star systems is more diverse than the neat gradients we drew from our few. Single example. When the parent stars and disks start with different carbon to oxygen ratios, or when heat rearranges materials early, you get families of worlds and small bodies that start weird by our standards and stay that way. Dust tells tales too. A carbon-forward environment tends to build grains that are darker and more conductive. That affects how they charge, how they clump, and how they scatter light. Polarization measurements of 3I Atlas hinted at dust that is not exotic beyond belief but also not bland. That fits a picture where the coma can carry currents efficiently, one more tick mark in the column that favors a magnetic cushion when a coronal front arrives. Chemistry and electrodynamics are not separate chapters. They are the same chapter written in different fonts. There is a forensic angle we have not fully exploited yet. Isotopes are the true fingerprints. Ratios of carbon-13 to carbon-12 and oxygen-18 to oxygen-16 carry the memory of the cloud and star that seeded the material. We cannot scoop a sample from an interstellar flyby, but high-resolution spectra sometimes carry enough detail to tease out isotopic hints. If 3I Atlas shows ratios that diverge from solar norms by a clear margin, we gain a compass needle that points toward older, lower metallicity nurseries in the thick disk, or toward regions stamped by nearby supernovae. That moves our story from maybe to more likely. Chemistry also sets the script for timing. Carbon dioxide sublimates at temperatures where water is still sleepy. That means activity can begin farther from the sun and stay strong at distances where a water-driven coma would be waning. It means the plasma factory is open for business during the very window when our visitor threaded near the sun's hidden hemisphere and the far side grew loud. If a magnetic cushion played a role, we would expect it to be most effective when the charge density is high. A carbon dioxide-driven coma delivers that at just the right time. There is a caution here. A single object is not a census. We need more interstellar visitors to see whether carbon forward is common or whether we met an outlier on a lucky night. That is why survey telescopes coming online will matter. With more samples, we can start to draw clusters in property space. Speed versus chemistry, tail temperament versus solar weather, sensitivity to small shoves versus activity distance. If a pattern emerges that links carbon-rich comas to strong ion tails and weak dynamical deflection, we will have turned a hunch into a rule of thumb. Until then, we can say this much without leaning on hope. The carbon dioxide dominance is not cosmetic. It changes how the coma turns sunlight into ions, how the dust carries charge, how the tail records shocks, and how any force from a passing magnetic structure is distributed. It also ties our small traveller to the big picture that Webb keeps painting. Planetary systems write different chemical poems. Our guest speaks one of those dialects. Listening carefully does not just solve a comet puzzle. It teaches us how varied the galaxy's recipes really are, and why the same physics can play out with different flavors when a star breathes and a wanderer passes close. Our star has seasons, and we are in the noisy one. Solar cycle, 25 climbed, faster and higher than early forecasts suggested. Sunspot counts ran ahead of schedule. Flares grew more frequent. Coronal mass ejections stacked in clusters. None of this is scandal. It is a reminder that a churning ball of plasma will not obey our tidy charts. We can predict trends. We cannot tell you which magnetic knot will snap on a given Tuesday, or how many fronts a single active region will launch before it goes quiet. That unpredictability matters for our story. A triple sequence of ejections from the far side during conjunction does not require a mysterious trigger. The cycle alone raises the baseline. Odds. When multiple active regions span wide longitudes, eruptions often arrive as flurries. If you draw any outbound lane near the Sun during a busy week, it is not rare for an expansion front to cross it. Coincidence is a stubborn rival to causation. The burden on a coupling idea is to show timing and geometry that beat chance, then to show comet-side responses that match those times. Solar physics gives us both humility and hope. Humility, because even with fleets of spacecraft, we still struggle to forecast when a particular loop will go unstable. Hope, because the same fleets give us exquisite statistics. We can count how often flares cluster. We can map how often far-side regions rotate into view, still gnarly after unseen tantrums. We can measure the distribution of ejection speeds and the likelihood that a front aimed in a wide cone will intersect a given distance within a given day. Those numbers let us score whether the triple overlap near our traveller was ordinary weather or unusually neat alignment. Cycle behaviour shapes front anatomy too. During active peaks, ejections tend to carry stronger fields and sharper shocks. Fast movers, the ones that chew through an astronomical unit in less than 2 days, become more common. Streamer belts bend and redirect fronts along preferred lanes. A front that might have diffused and softened in a quiet year can stay coherent longer in a hot one. That raises the stakes for any small body in the path. It also sharpens the signatures we should hunt in ion tails. Stronger fronts stamp cleaner compression waves and produce more dramatic disconnections. There is a lesson about forecast here that extends beyond our visitor. The models we use to predict space weather are part physics, part boundary conditions, part art. We feed them magnetograms, coronagraph speeds, and wind measurements from a few points, then ask them to guess a three-dimensional future. During a noisy cycle, those boundary conditions change faster, and the art matters more. That is why an interstellar comet is not a sideshow. It is a tracer particle in a turbulent flow. If it records the shock structure cleanly, it becomes a moving probe of a system we need to understand to protect satellites and grids. The mid-cycle jolt of an extreme flare earlier in the year drove this home. An eruption many expected to be modest detonated into one of the stronger events of the decade. Radio blackouts flared on Earth's daylit side. Auroras spilled far toward the equator. Spacecraft reported glitches. The lesson was not that models failed. The lesson was that the sun reserves the right to surprise. Soft probabilities can stack into a hard event without violating any rule. When that mindset becomes habit, you stop asking whether 3 far-side ejections are unbelievable and start asking how precisely we can time them and what fingerprints they should leave. It also reframes skepticism. If the post-conjunction orbit is tight and tails do whisper, in step with distant eruptions, the cushion idea does not need to argue that the sun behaves strangely. It only needs to argue that a lively coma met ordinary violence and redistributed the push. If the orbit kinks, the cushion can fall back to a supporting role, while missed fronts or mass win the lead. Either outcome is consistent with a cycle that is louder than first advertised. Looking forward, the peak will not last forever. Activity will crest, then taper over a few years. That arc sets an observation plan. Now, while the star is boisterous, we should harvest cases where comets and fronts rendezvous, interstellar or local. Each encounter calibrates how tails encode shocks and how often nuclei drift. When the cycle fades, we will have a baseline to compare. Did the cushion only appear during the loud season when charge densities and front strengths ran high, or does the effect persist in quiet air? So yes, the sun is hotter tempered than the early charts claimed. That does not solve our paradox, and it does not break it. It sets the stage and raises the background odds. The perils of prediction in a busy cycle force us to trade certainty for discipline, count eruptions, time waves, measure positions, let statistics tame the drama. In that work, a small traveller becomes a clear mirror for a large, restless star. If you want to know what a small body can hide, ask a rock that has been to the lab. The samples from asteroid Bennu and asteroid Ryugu rewrote our expectations about what lives inside a rubble pile. Under microscopes, the grains showed hydrated minerals that formed in contact with liquid water long ago. Tiny flecks gleamed brighter than their surroundings, hints of metal-rich inclusions mixed into darker matrices. Elemental ratios wandered from one speck to the next. The message was simple and disruptive. Small bodies are not uniform snowballs or monoliths. They are mosaics. That mosaic matters for our mystery. A nucleus a few kilometers across can be a layered cake of densities. Porous outer rind, tough interior clasts, possibly pockets where compacted rock or metal concentrates mass. Seen from afar with a single brightness number, you infer one average size and one average albedo, then you back out a mass that assumes fluff. If the core is denser than the shell by even a modest factor, the true mass climbs without advertising itself in the light. The comet can carry more inertia than the brightness suggests, while still bleeding gas in a lovely carbon dioxide forward coma. Laboratory surprises do not stop at density. The Bennu and Ryugu samples carry pre-solar grains, dust older than our sun with isotopic fingerprints from red giants and supernovae. That tells us that small bodies can preserve wildly different source materials side by side, each with its own radiation history and mechanical strength. Translate that to an interstellar visitor, and you get permission to consider a nucleus with a hardened interior, a tougher plate under a powdery crust. Momentum delivered by a passing front can burrow into that plate and spread, leaving the center of mass barely moved. We also learned that rubble piles flex. Ryugu and Bennu both have boulder fields that can shift when nudged. On a comet, the analog is gas-laden regolith that puffs and settles as the sun turns the day side on. Energy and force can go into rearranging grains rather than pushing the whole body. Think of a beanbag that deforms when slapped but slides only a little. The more complex the interior, the more channels exist for a shove to dissolve into heat and shape changes. None of this lets us hand-wave. It gives us new tests. If hidden mass is real, the nucleus should rotate in a way that resists big swings when outgassing jets turn on and off. The spin rate should drift slowly, not whip around. Thermal inertia inferred from infrared light should hint at compacted material below a looser skin. Radar echoes, if the geometry ever allows, a bounce should come back with sharper glints than a pure snowball would give. Even subtle clues help. A coma that keeps a steady inner shape under changing solar angles can point to a nucleus whose gravity is a bit stronger than its size implies. Meteorites back on Earth add another line. Iron-rich fragments survive entry more often than fluffy, carbonaceous material. Their magnetic properties can persist for billions of years. If interstellar debris shares that trait, then a metallic clast inside a cometary body is not science fiction. A core that carries remnant magnetization could add a stitch of self-generated field to the coma. One more way to stiffen the magnetic cushion when a coronal front arrives. You do not need a dynamo. You only need enough aligned domains to matter across a few kilometers. Sample return from an interstellar visitor would settle arguments in an afternoon, and right now, it sits in the realm of hard dreams. We can still borrow sample return thinking. The lab taught us to respect heterogeneity. The lab taught us to let isotopes arbitrate origin stories. The lab taught us that a small change in grain makeup can mean a large change in bulk behavior. Those lessons push us to design observations that are sensitive to patchwork interiors rather than to averages. More nights of precise positions, more attempts at thermal mapping as the object fades. More patience looking for small, repeatable drifts that betray a heavier heart. There is a philosophical shift here. The old picture said a comet is a type and that type behaves within a narrow band. The new picture says each traveller is a portfolio of materials and histories, and that portfolio determines how forces are absorbed and expressed. In that picture, it is not shocking that a carbon dioxide-rich body with a sturdy inner clast could hold its line under a storm that would nudge a fluffier cousin. So, when we weigh the conventional outs, hidden mass moves from a hand wave to a candidate, with teeth. Not an iron cannonball, not a trick, simply a layered world the size of a town that inherits density from a past we cannot see. Bennu and Ryugu taught us to expect that. Meteorites taught us to expect that. If 3i Atlas took a punch and barely budged, a stronger spine under a soft face is a story the rocks already know how to tell. This is the window that decides whether the story is odd or ordinary. The visitor is past closest approach and bright enough for careful work under dark sky. Every fresh position you measure now either tugs the orbit line away from the pre-conjunction path or stitches it tighter. Every deep exposure either reveals ripples in the ion tail at the right times or shows a coma that refuses to flinch. 20 nights is enough to turn hunches into evidence if we spend them well. Begin with the ruler. Astrometry wants routine. Same telescope fields, same reference stars, same reduction pipeline. Measure the stars first, fit the plate, then the target. Log seeing, wind, and any guiding quirks. Do not chase a last half-arc second by changing everything at midnight. Consistency beats heroics. A clean sequence of positions night after night gives the orbit fitter a time base long enough to iron out small nightly biases. If a shove landed during conjunction, the residuals will drift in one direction with a calm you can feel. If not, they will sit inside the noise like a cat in a patch of sunlight. Pair the ruler with a stethoscope. Use narrowband filters that favor common comet ions, so the ion tail stands out from dust. Aim for long, steady integrations to bring out low-contrast structures without amplifying noise. When you can, book 2 looks per night separated by a few hours. Shocks write their timing into the tail as waves that start near the coma and walk outward. 2 snapshots give you a slope on a distance versus time plot for those features. The slope should land near a reasonable local solar wind speed. If the whoa, compression is real. If the slope is nonsense or absent, the cushion case loses air. Add polarization where possible. Even a modest instrument can measure changes in the way the coma scatters light when it compresses. Take a baseline on a quiet night. Repeat during suspected solar arrivals. A small, consistent swing that relaxes later is a signature that currents and grain alignments changed under pressure. No swing does not kill the idea, but a swing strengthens it. Coordinate north and south. The object is fading. Weather will steal nights from every site. Spread the risk. Mix amateur observatories that can give you long runs with professional facilities that can go deeper. Ask for honesty about limits. A precise null result is gold. A maybe that cannot be reproduced wastes time. Share raw frames and calibration files so others can rerun reductions. The goal is not a single pretty image. The goal is agreement among strangers. Keep one eye on the star. Archive the times and rough speeds of any new coronal ejections from solar monitors. Note when the active regions that were loud on the far side rotate into view. If a front leaves today, estimate when a shock would cross the traveller's lane and plan deep exposures for that window. If an active region reappears looking shredded and mean, expect more fronts and schedule accordingly. A tail that stiffens within hours of those predictions argues for coupling. A tail that ignores even well-aimed fronts argues for quiet physics and near misses. Fold in rehearsal. Run simple simulations that span the plausible range of nuclear size, mass, and outgassing thrust. Let virtual fronts with plausible speeds pass by at the measured angles. Ask how often a measurable offset would appear downstream. If the answer is almost always, even a handful of tight post-conjunction nights is decisive. If the answer is rarely, demand a longer baseline before you draw lines in ink. Watch the spin. Short exposures near the nucleus can pick up repeatable jets that beat with rotation. If outgassing thrust changed during conjunction, that beat should have changed character too. A stable clock before and after conjunction weakens the idea that a rogue jet faked a small one-sided shove. A clock that stumbled right when offsets appeared points back to the nucleus itself, not the Sunday. Most of all, pre-commit. Before you reduce tonight's data, write down the threshold that would count as a real kink over the next 2 weeks. Write down what kind of tail wave would count as timed and structured rather than random flicker. Then hold yourself to your own rules. The fastest way to clarity is to make the test hard on your favorite outcome. If the ruler stays straight while the stethoscope hears ripples in step with solar breath, the magnetic cushion moves from clever story to working tool. If the ruler bends with calm inevitability and the tail does nothing special, a missed fronts or hidden mass take the lead. If neither, ruler nor tail, says much, the safest answer wins by default. Either way, 20 well-spent nights will give us what we came for. Not drama, truth. When a story crackles, add-ons multiply. A traveller near the sun, a burst of eruptions, a full moon looming on the calendar, and suddenly you hear whispers that geomagnetic storms plus lunar tides equal earthquakes. It sounds tidy. It is also the kind of chain that our brains love and data does not. If we are going to keep this investigation honest, we have to cut cleanly between effects we can measure and tales that feel right because they rhyme. Begin with what is solid. Solar eruptions can drive geomagnetic storms at Earth. Those storms bend our planet's magnetic field, pump energy into the upper atmosphere, and rattle the ionosphere. Satellites feel drag and radiation. Radio links fade. Power lines hum with induced currents. All of that is real and repeatable. The moon's gravity lifts the oceans into tides that tug at Earth's, crust by a hair. Those solid Earth tides are small. They wax and wane like clockwork and, in a few specific fault geometries that are already close to failure, can nudge timing by hours or days. That is not rumor. It is a subtle statistical tilt seen in careful studies. Now, stack the claims. A far-side blast supposedly aligned with our visitor. 2 weeks later, those active regions face us. A full moon lines up. People connect dots and ask whether the stack raises earthquake risk. The problem is that each dot is weakly connected to the next, and the stack does not multiply strength. It multiplies uncertainty. Geomagnetic storms live in the sky and currents in wires. Faults live in rock at depth. The bridge between them is conjecture, and if it exists at all, it is so faint that it disappears inside the natural variability of a noisy planet. How would a real link look if it were there? You would see a consistent increase in earthquake rates above magnitude thresholds during windows of strong, well-characterized geomagnetic disturbance after removing seasonal, regional, and catalog bias. You would see the effect survive corrections for aftershock sequences. You would see it persist across multiple catalogs and decades, with pre-registered tests that do not chase significance after the fact. You would see plausible physics, a mechanism that carries energy from the magnetosphere into stress changes at fault depth with magnitudes that are not laughably small. We do not see that suite. We see anecdotes that pick a storm and then point to any quake that happens to occur, which is often because earthquakes often. The moon part of the stack deserves nuance. Tidal stresses can advance the clock on some thrust faults by a whisper. That whisper does not summon quakes from nothing. It is a timing nudge, not a causal engine. When people propose a supermoon crisis, they amplify a tiny effect into a forecast that cannot cash the check. The right public message is boring and useful. Expect higher tides and pretty sky photos. Expect nothing special from the faults under your feet beyond the background risk that never sleeps. There is a deeper reason to police these leaps. When we borrow credibility from a real phenomenon to prop a weak one, we make it harder for the real warnings to land. A geomagnetic stormwatch is about satellites, power grids, and radio links. It is not about buildings swaying. Mixing those messages confuses operators and the public. It invites cynicism when the promised drama does not arrive in the wrong domain. If you care about readiness, you keep the domain separate and the claims modest. What would change my mind? A mechanism first. Show that magnetic field variations of realistic amplitude can drive currents in the crust large enough to alter pore pressures at seismogenic depths by meaningful amounts, and show it with lab measurements and in situ geophysical logs. Then a pattern. Pre-register a test on decades of global earthquake catalogs with a hard threshold for what counts as an effect, and publish whether the test passed. If it does, I will happily update. Until then, the honest answer is that space weather and quakes inhabit different rooms, and the thin corridor between them looks empty. So where does that leave our traveller? Right where it belongs, inside a story about plasma and light, not omens and fate. A carbon dioxide heavy coma can couple to solar fields. A magnetic cushion can turn a shove into shape and heat. A tight downstream orbit can survive a loud week on the far side. All of those claims live in telescopes and coronagraphs and magnetograms. They do not need moonlight or fear to feel urgent. They have urgency because they teach us how a star shares energy with its environment and how small bodies record the exchange. If we keep our curiosity tethered to evidence, we gain twice. We protect the credibility of the warnings that matter on the ground, and we keep the wonder of the sky anchored to the measurements that make it science instead of myth. The traveler is not here to fix our superstitions. It is here to show us what physics does when a wanderer meets a restless star. That story is already more than enough. Here is how this story can end without closing the book. The orbit line either holds or it bends. The tails either whisper in step with solar breath, or they stay quiet under every predicted arrival. The active regions that raged on the far side either roll into view scarred and loud, or they saunter around the limb like spent fireworks. Each fork answers a different question. None of them exhaust the mystery, because the deeper thread is not a single verdict. It is the way a small, swift traveler turned our star into a laboratory and dared us to measure better. If the ruler stays straight while the ion tail shows timed ripples, we add a page to the playbook with ordinary physics written in an extraordinary hand. A carbon dioxide forward coma, rich in charge and dust, behaved like an induced magnetosphere. Magnetic pressure turned push into shape and heat. The nucleus coasted. That is not a loophole. It is a mechanism. It says that in a busy solar cycle, some small bodies will record the storm in their tails rather than in their paths. Forecasting improves. Space weather models inherit a fresh constraint. The romance remains, but it now pays rent. If the ruler drifts with calm inevitability and the tail offers no special choreography, we learn a different lesson with the same value. Near misses and hidden mass can masquerade as paradox at the edge of glare. A denser heart beneath a softer face can carry more inertia than brightness suggests. The sun's fronts are frothy quilts, and alignment does not guarantee a clean hit. Our tools become humbler. We ask for longer baselines and tighter error bars before we call anything unthinkable. We still win, because the next object will be judged with clearer eyes. If nights slip away and the evidence refuses to lean, that too is an answer. It says our cadence was too slow, our angles too few, our patience too thin. It is a nudge to build the infrastructure we wished we had this time. A coronagraph built to track faint movers, not only coronal loops, a dedicated far-side sentinel, a rapid response pipeline that can point narrowband cameras within hours of a posted ephemeris. Wonder is not a substitute for investment. It is the fuel that makes investment feel urgent and shared. Either way, 3i Atlas changes how we look at the sky. It stitched together the personal and the cosmic. A community of amateurs with careful logs, shared fields with orbital observatories that dream in ultraviolet. Machine learning filtered the glare while humans argued about error bars. The sun sang through heliosismology, while a smudge of reflected light kept an appointment with a line of stars. That is the modern shape of discovery. It is messy, distributed, and stubbornly empirical. It is also the best antidote we have to myth. The road ahead is not empty. Survey telescopes will find more interstellar visitors, and sooner than you think. Some will be dry and quiet and still drift. Some will be loud with water and behave like cousins we know. Some will write in carbon the way this one did, and give us another chance to watch a magnetic cushion at work under a different geometry. Each will force us to recalibrate where wonder ends and measurement begins. That recalibration is the point. It is how a field matures without losing its spark. We also owe ourselves a promise to make predictions before we peak, to publish the thresholds that will count as real, to celebrate null results as loudly as showy detections when they close doors we were tempted to keep ajar, to welcome citizen data with the same rigor we apply to our own, to keep speculations on their leashes until data give them teeth. That culture is harder than a headline. It is the only way the next headline deserves attention. So here is the call. If you want to ride along as we chase the next interstellar visitor, subscribe and stay close. If you learned something tonight, share this with the one friend who will argue with you about it and make you sharpen your case. Tell us where you are watching from and what the night sky looks like there. Curiosity grows in company, and this channel is built for that company. The traveler is already fading into the dark. The sun will keep its cycles. Our detectors will get faster, our models more honest, our patience a little longer, the universe will keep throwing us objects that do not quite fit until we make room for them. That is not a bug in science. It is the feature that keeps it human. A small rock from another star system crossed our sky and made us better at looking. That is enough for tonight. Tomorrow we measure again.